This video is brought to you by the UBC Molecular Mechatronics Laboratory. Learn more about us at mm.ece.ubc.ca. My name is Zi Chen. This will be the first of a series of tutorials that will help you understand the manufacturing processes of a flexible capacitive sensor. This video covers the production technique used to produce a multi-layer flexible PCB. Using copper sheets and a 3M high-temperature resistance flexible substrate. The general idea goes as the following. 3M tape is placed onto the copper foil, and the layers are stacked together to form our multi-layer PCB. The first step in making a 3-layer flexible PCB is to create a printable mask using Altium. As you can see, I have my Altium designer opened and the project file ready. Open the PCB document, view configuration, add a new mechanical layer named negative. Using Shift S to select this layer. Go to Primitive, select Fill, and draw a rectangle covers the entire PCB. Since we are using negative photoresist, this is going to be the background. This step is not required for positive photoresist. Our PCB document is now ready. Create an output job file by right-click on Project, add New to Project. If you already have an output job file, then just open it. Add a new composite PCB document under Document Output. Give it a name. Right-click and go to Configuration. 3 composite layers are needed for a 3-layer PCB. Right-click to add 2 more layers. Now we have to add the layer stack sequence. Order of the layers matter. It is equivalent to stacked sheets of paper. The final image is a combination of stacked patterns. L1 and multi-layer are trace layers, so they always goes to the very top. Negative layer is a background, so it goes to the very bottom. Outline and other features are sandwiched in the middle. Now I have finished configuring all the layers. Mirror all the layers to enhance production quality during the exposure process. After mirrored all the layers, go to Preferences and edit Layer Color. Since we are using a negative photoresist, white color will be copper and the black color will be etched away. Therefore, all trace layers, such as L1 and the multi-layer, should be white. Negative is a background layer, so it is black. Outline and other features may be either black or white depending on the situation. I used the black outline in this case. After configuring all the layers, right-click on the document and click Page Setup. Choose Scale Print and set to 1:1 ratio. This will ensure the PCB dimension is correct. Use color or gray, never use mono. Click Document Preview to inspect each layer. Remember, if you are using negative photoresist, the copper will be white and the black portion will be etched away. When you are finished, go to Page Setup again and choose Print. Always print directly to the printer. Never ever print the document to a saved PDF format and print later. Oftentimes, saved PDF applies a small scaling factor to your print, even if you select 1:1 print ratio. First, print your design onto a piece of paper to inspect any significant error. If the patterns are correct, load the transparency into the printer. Always use the transparency for laser printer only, as it does not warp when heated up by the laser printer. Visually inspect the mask to make sure it is free of defects. Check the mask under the microscope to make sure it is perfect. This is an example of a defective mask. As one can see, a blemish appeared on the region of the polygon pore. This mask needs to be reprinted. Trim the mask to a manageable size. This is the finished result. Cut the 3M tape and copper sheet so that it can cover the entire mask area. Tape the copper sheet onto the table so that the protective layer faces upward. This step ensures that the copper sheet does not warp when the adhesive is removed. Remove the protective cover on both the copper sheet and the adhesive. Gently guide the adhesive onto the copper sheet. Use your finger as a squeegee to ensure no air bubbles are trapped. Fold over the excess copper or trim it away. This is the finished result. The following procedure is a 2-person's job. Cut the photoresist to roughly the size of the letter paper. Remove the protective cover by using 2 pieces of tape. Tape one edge of the photoresist onto the paper. Place a copper sheet under the photoresist. Turn on the laminator. Set the speed to 1 and temperature to 110 degrees Celsius. One person is going to feed the sheet through the laminator, while another person is going to apply tension to the photoresist. This will ensure that the lamination is wrinkle-free. Cut out the copper sheets after lamination. This is the finished result. Clean the glass slide, make sure it is dust-free. Sandwich all the components together in the order of glass, mask, copper, and glass, from top to bottom. Clamp everything securely. Expose the photoresist under UVA for exactly 1 minute and 10 seconds. You may have to experiment with the timing a bit if you have different UV lamp, photoresist, or glass slides. Retrieve your sample once the exposure is finished. There should be a visible pattern on the photoresist. Prepare the baking soda solution. Use roughly 10:1 ratio by volume. Remove the top protective cover from the developed resist. Place it into the baking soda solution. You should see the color of the photoresist slowly turning white. Remove it from the solution after 2 minutes. Rinse the part. It will begin to reveal the shiny copper underneath. Inspect the part under the microscope to ensure it is free of defect. Place a large beaker onto the hot plate. Make sure the stir bar is working properly. Pour the iron chloride solution into the beaker. Add the same amount of water to dilute the solution. Turn on the heating and the stir bar. Carefully place the copper sheet into the solution so it can float using surface tension. Check regularly until all the exposed copper is removed. Rinse the part. You should not see any visible copper at this stage. Check under the microscope. Take special notes for bubbles like this. This is caused by the defect in the photoresist. The copper underneath is not protected, and this sensor should be rejected. Here is the finished product. Cut the unwanted area defined by the board outline. You might need a variety of different tools to help you accomplish this task. I am using a leather hole puncher to punch the holes, and using a craft knife to cut the straight edge. After cutting, we are left with a component for 2 sensors, and we are ready to assemble them. Residual photoresist needs to be removed before assembly. Create a 1% sodium hydroxide solution by weight. Make sure that you have enough solution so that the PCB is completely submerged. You will see the photoresist peeling off and reveal the shiny copper underneath. Rinse the part. Dry it in the oven. One final inspection before assembly. We now have all the required components, and we are ready to assemble our multi-layered PCB. First, remove the protective cover from the ground plane. We did not wear gloves for this procedure because the 3M tape will stick to the glove and make this procedure extremely difficult. Hand wash and work surface sanitization are performed after this procedure to conform with COVID guideline. Safety of the workspace is always held as the highest priority. The ground plane is carefully placed onto the trace plane, with the help of the guide rod to ensure accurate alignment. Use your hand as a squeegee to ensure proper adhesion. We now have our finished product. I hope you have learned something useful and understand the key concept in making a multi-layer flexible PCB. Thank you for watching.